Today we are going to learn about mastering text preprocessing for classification, focusing on essential techniques to clean and transform text data, improving model accuracy and performance.
Welcome to our session on mastering text preprocessing for classification. In this video, we'll explore why preprocessing is a critical step in building effective text classification models. Text preprocessing involves cleaning and transforming text data, which, in turn, enhances the accuracy and performance of our models. By the end of this video, you'll be equipped with practical skills to clean, normalize, and convert text data into numerical features, setting a strong foundation for improved classifier results. Let's dive into the world of text preprocessing and unlock the potential of your text data.
Text normalization is the process of converting text to a standard form, crucial for ensuring consistency and comparability in text data. It involves several techniques such as lowercasing, where we convert all text to lowercase to avoid treating data and data as different entities. Another technique is removing extra white spaces, as inconsistent spacing can lead to misleading word boundaries. Text normalization also involves standardizing abbreviations and expanding contractions, ensuring uniformity across datasets. By applying these methods, we create a clean slate where every piece of data is consistent, paving the way for effective text classification.
Tokenization is the process of splitting text into individual units, like words or sentences, making it easier to analyze and process. Word tokenization breaks down text into words, while sentence tokenization splits text based on sentences. This step is foundational for many NLP applications as it allows us to work with manageable pieces of data. Tools like NLTK and SPA-SCI in Python offer robust tokenization functionalities. However, tokenization isn't without challenges, such as handling contractions or ensuring tokens preserve context. Mastering tokenization is key to effective text data handling and lays the groundwork for subsequent preprocessing steps.
Stop words are common words like and, the, and is, which often carry little meaningful information for text classification tasks. Removing these words helps to reduce noise and improve the quality of features extracted from text data. By filtering out stop words, models can focus on more relevant words that contribute meaningfully to the text context. Libraries such as NLTK, SPA-SCI provide lists of stop words and functions for their removal. While removing stop words generally boosts performance, it's essential to consider the specific application, as some tasks might benefit from retaining certain stop words.
Stemming and lemmatization are techniques used to reduce words to their base or root form, which standardizes text data. Stemming involves cutting off prefixes or suffixes, often resulting in non-dictionary forms, while lemmatization considers the context and converts words to their dictionary form. For instance, running becomes run in both methods, but stemming might result in room. Lemmatization is more accurate but computationally intensive. Choosing between them depends on the task at hand, with stemming suitable for applications requiring speed, and lemmatization for those needing precision. Libraries like NLTK provide easy access to both methods. Special characters and punctuation marks can clutter text data and potentially distort analysis results if not handled properly. Removing unnecessary punctuation helps in reducing noise, but it is imperative to recognize when punctuation carries meaning, such as in contractions or emoticons. Techniques for handling punctuation include regular expressions for pattern recognition and removal or transformation. Libraries in Python, like regex and re, offer powerful tools for managing special characters. Proper handling ensures cleaner, more interpretable data, facilitating better model performance and accurate text analysis.
Misspellings and typos are common in text data, especially user-generated content, and can significantly impact model performance by introducing noise. Techniques to address this include spell-checking algorithms and edit distance calculations. Libraries like hunspell and textblob in Python offer tools for automatic correction. However, challenges exist, such as context-dependent corrections, where the intended word might differ based on the surrounding text. Correcting these inaccuracies improves data quality, ensures consistency, and enhances the reliability of text classification models. TF-IDF, or term frequency inverse document frequency, is a statistical measure used to evaluate the importance of a word in a document relative to a collection of documents. It transforms text into numerical features by considering how frequently a word appears in a document compared to its appearance across all documents. This method emphasizes unique words that contribute meaningfully to the text context, improving model performance. While TF-IDF is powerful, it assumes term independence and doesn't account for semantic relationships. Libraries like scikit-learn in Python provide efficient implementations for transforming text data into TF-IDF vectors, aiding in robust text classification tasks. Handling large datasets presents unique challenges in text preprocessing, such as increased computational demands and memory constraints. Best practices include optimizing preprocessing pipelines with efficient algorithms and leveraging scalable frameworks like Apache Spark for distributed processing. Techniques like batching and streaming can aid managing large volumes of data. It's also crucial to consider efficient data storage formats, such as Parquet or ORC, which support fast data retrieval. By adopting these practices, you can efficiently pre-process large datasets, ensuring that your text classification models remain performant and scalable.
As you advance in text preprocessing, you'll encounter scenarios requiring techniques beyond the basics. Advanced normalization might involve handling domain-specific jargon or applying custom text transformations. Custom tokenization can be employed to parse complex text structures, such as code snippets or log files. Similarly, domain-specific stop words can be identified and removed to enhance feature quality. Handling complex text structures, like nested comments or multilanguage documents, demands innovative approaches and potentially customized scripts. By expanding your toolkit with these advanced techniques, you'll be able to tackle diverse text data challenges with greater precision and efficiency.
Evaluating the impact of preprocessing on model performance is essential for optimizing text classification tasks. This involves measuring changes in accuracy, precision, recall, and F1 scores after applying preprocessing techniques. Iterative experimentation is key, as different datasets may benefit from varied approaches. By systematically testing and comparing preprocessing pipelines, you can identify techniques that yield the best results for your specific application. Continuous improvement through feedback loops ensures that your models remain robust and effective, adapting to new data and evolving requirements. This evaluation process is crucial for refining preprocessing strategies and maximizing classifier success. In conclusion, mastering text preprocessing is a vital step in building effective text classification models. We've covered essential techniques, from normalization and tokenization to dealing with misspellings and converting text into numerical features. Each step plays a significant role in improving model accuracy and performance. Remember, preprocessing is not just about cleaning data, it's about transforming it into a form that maximizes your model's potential. We encourage you to continue exploring and experimenting with these techniques to enhance your skills further. Thank you for joining us, and we hope you find success in your text preprocessing endeavors.